Okay, this one is similar to an earlier example we did, but this one is going to be a little bit harder because when I do the Pythagorean theorem here, I'm not going to get a pretty little whole number like I got last time. So when I do the 5 squared, 4 squared, that's 25 plus 16. And 25 plus 16 is 41, and 41 is not a perfect square. So it's not going to end up being a whole number like the previous example that we saw. So it's also not reducible, meaning there's not a perfect square that divides 41. So when I go to do sine, sine is opposite, so there's our angle. Opposite is b, so that's this 4 over here. 4 over the square root of 41. Because we have a radical in the denominator, that's not simplified. So we want to simplify it by rationalizing the denominator. That means I'm going to multiply the bottom and the top by that square root of 41. And what that does, the square root of 41 times itself is 41. That's what it means to be the square root of 41. That gets a denominator that's no longer a radical. And in the numerator we have 4 times the square root of 41. So that's how we would simplify the sine function in this case, and that's why it makes it much more difficult than if the square root of 41 just ended up being, square root of 4, and ended up being a whole number. But in this case, we have to do that rationalization process anytime our square root is in the denominator. If it's in the numerator, it's okay, but for the denominator, we would need to get do this rationalization process. All right, cosine is adjacent over hypotenuse, so that's going to be the a, which is 5 over the square root of 41. If I flip those over, I'll get secant and cosecant, meaning I flip these over. So this, the reciprocal of this is what I'm going to use to get secant and cosecant in just a little bit. All right, but I'm going to have to do the same process as before. I'm going to multiply the top and the bottom by the square root of 41. All right, that's going to give me 41 on the bottom, and then instead of 4 square root of 41, now it's 5 square root of 41 on the top. So there's sine, there's cosine. Tangent is opposite over adjacent, so that's the b over a, so that's 4/5. And notice, just like before, it was the numerators of sine and cosine. All right, before we did the rationalization process, 4, 5. All right, it's also the numerators here, 4 square root of 41 over 5 square root of 41, and those square roots of 41s would cancel. So that still holds. That property is true universally. It's just easier to see it with just the side lengths themselves in this case. All right, and now it's the other three. So for cosecant, I'm going to work on that boxed in version of sine that I have. I'm going to flip this over, and I'll have the square root of 41 on the top and the 4 on the bottom. And because the radical's in the top, I don't have to do anything else. No need to rationalize. For secant, let's flip this one over. So the square root of 41 over 5. All right, so there is the process of finding those 6 trig functions when the hypotenuse happens to be a radical that we can't simplify.